Hi, everyone. I am Margarida Rodriguez, HPP Application Specialist at Hyperbaric Spain. I would like to welcome you all to a new session of the HPP Innovation Week titled High Pressure Thermal Processing, HPTP, versus Thermal-Only Processing, Industrial Implementation, Food Safety, and Quality. In the next minutes, we will learn about this exciting technology. Firstly, with Dr. Kai Knauser. He's from CSR in Australia. He will talk about the device. Hi, Kai. He will talk about the device, the insulated canister he developed and patented so that we can reach to a commercial step with this technology. And then we will welcome Dr. Robert Savanich. Hi, Robert.
Hi.
From the Technical University of Berlin, Robert will talk about food safety and quality aspects, highlighting the differences between HPTP and thermal processing. Thank you both for being here today with us. I'm going to start by introducing Kai. So Kai is a principal research scientist in CSR Agriculture and Food, a renowned scientific and industrial organization in Australia dedicated to solve the greatest challenges through innovative science and technology. For the last years, Kai has been working in a patented multi-layered canister to be used in HPTS. He presented the technology to Hyperbaric, and for the last 2 years, we have been working together towards its validation and commercialization. In fact, from Hyperbaric, we have installed in 2009 a prototype machine combining high pressure up to 120 degrees, under pressure up to 600 megapascal, in a technological center in Nazi, Bilbao, here in Spain. This machine does not use this technology, the canister. It has a temperature-controlled vessel, being very hard to maintain the hot vessel because we have some gradients throughout the vessel. HPT performed several studies using fish products to inactivate spores with very interesting results, even up to 90 degrees. Whereas the solution here presented distinguishes greatly since we will use a multi-layered insulated canister, avoiding the problems related with temperature gradients. With this being said, Kai, if you feel so, the floor is yours. Thank you.
Thank you very much. All right. Thank you, Margarita, for the very kind introduction. You took away a lot of the stuff I wanted to say in my talk, but that's okay. I'll just repeat it. Just checking, can you see the slides all right?
You can start.
All right, good. Thank you again. And welcome everyone to my presentation on making high pressure thermal processing a commercial reality. Now here on this slide, you can see the outline of my talk. I will start with articulating the problem. What do we have? Why is high pressure thermal processing not used at commercial scale just yet? I will then talk about our approach to solve this problem, initially presenting a couple of tools we have developed to assist us in this approach. The first one, compression heating properties of plastics and how can we measure them. The second one, measuring temperatures under the harsh high pressure thermal processing conditions. I will then introduce the concept of an insulating canister, the one that Margarita talked about in her introduction, and then have a few slides on the validation of that concept at pilot scale and also at commercial scale. And I will finish off the presentation with a short summary and an outlook on where we are heading next. Now, the problem, what is it? Well, as we have heard before, there are not many pilot scale systems with high pressure thermal processing capability available worldwide. There's a handful maybe, one at ASTI, another one here at CSRO in Australia. They range in size from 35 to 55 liters. They come from various manufacturers. There is, to the best of my knowledge, one larger system up to 150 liters that exists. However, there is significant temperature variation throughout the vessel, so that seems to be the biggest problem, which is why that can never be used for a high-pressure thermal process, for a safe high-pressure thermal process. But even at lab scale, and as Margarita mentioned before, pilot scale systems, they also show those significant temperature variations. So bottom line, there's no commercial scale system available that can fulfill the requirements for safe high-pressure thermal processing. Now coming to the solution. So as I said before, we first developed some tools to assess material and process performance, and then we used those tools and the know-how we developed to develop an alternative to a dedicated high-pressure thermal processing machine. I'm starting with the pressure and temperature dependent compression heating properties. This is a busy slide. I'm not going to go into too much detail here. If you are interested about the approach, there's at the bottom of the slide, you can see a reference to a journal publication. That one here is on plastics, but there's another reference in that paper then that refers you to the another study on compression heating properties of liquids. So the approach we developed, or the methodology, is applicable to liquids, semi-solids, and solids. It's slightly different in experimental setup. The top one here shows the setup for, or schematic of the setup for liquids. At the bottom, you can see the one for solids. What we do then is we run a high pressure thermal processing cycle at different initial temperatures. Once we reach the end of the pressure hold time, we record the pressures and temperatures at a very high acquisition rate. And the reason why we chose the decompression part of the process is because it is very fast and it's near adiabatic. So what we do then is we take all these values, the pressure and temperature values, we plug it into this differential equation, well, actually the reverse of that differential equation. This one describes the temperature change upon pressure change under adiabatic conditions, and most of you will have seen that already in one form or another. So we crunch those numbers through that algorithm, and what we then get is equations that describe the compression heating properties as function of pressure and temperature, shown here at the top, and an example for water at the bottom for polyethylene. So what we do then is, once we have these equations, we put them back into the differential equation, and we can then predict the adiabatic temperature increase for any initial temperature and any pressure level. We looked at various substances, propylene glycol, polyethylene, polypropylene, Teflon, many other plastics and liquids, and water as well. So water, as some of you may know, is this data has existed for a long time as part of the NIST database. So we measured it for water anyway, just to make sure that our approach is valid. So we compared the NIST database values with our measured values, and they agreed well. So then we went further and looked at all these other materials and liquids. So as you can see, they all look very different. None is like the other. Solids, very different behavior to liquids, but even among the liquids, there is a big difference. We then looked at, so in this upper range here, which is relevant for pasteurization and sterilization temperatures, we looked at what plastic is actually sort of in the range of water, and we found that polypropylene is quite close. Teflon heats up to a lesser extent than water, and any food product for that matter, and polyethylene heats up more than water, and that becomes relevant when we talk about the concept of the insulating canister. Now, coming to the next tool, as I said before, it is important to measure temperatures in high pressure thermal processing. We need to understand the temperatures throughout the process. So that is very relevant with respect to processing and process validation, but also for our purpose to validate the concept of that insulating canister. So being able to actually measure temperatures within the canister space. Thermocouples have been discussed and used previously, but what we found, especially at least, is that they tend to fail after a limited number of runs. The readings can be disturbed for any reason, really. And especially when we then think of application in a horizontal industrial scale machine, it's very hard to implement thermocouples in that setup. So what we came up with, we call the thermo egg. It's really pressure resistant shell made from aircraft aluminium. And within that shell, we have a commercially available data logger. So the shell, highly stress resistant, low specific heat capacity, high thermal conductivity, and the data logger has a wide temperature range from 0 to 130 degrees C and can measure temperatures in 1 second intervals. What we found fairly early in that study is that while we have high thermal conductivity, there is still a lag delay in the heat penetration. So what we measure actually inside the egg is not what you would expect to see in the high pressure thermal process with very fast temperature changes during compression and then during compression and decompression. But we applied a clever algorithm that now lets us predict the temperatures outside the shell from the delayed readings within the shell. And again, if you're interested to learn more about that, details around the algorithm and the design of the thermo egg, there's a reference at the bottom of the slide here. So coming now to the concept of this insulating canister we heard about before as an alternative to a high pressure thermal processing machine. Now the concept here, as you can see, it's multi-layered. We developed that to facilitate high pressure thermal processing in a cold or conventional high pressure machine. A multi-layer because there are many reasons why you have cool down during a high pressure thermal process. it's not just insulation. It's also what is in the product, what are the in the canister or carrier, what are the compression heating properties, etc. So this multi-layer approach we have chosen is, so the outermost layer, it doesn't have to be a high compression heating property, so it can be lower than your water or your product in the canister, but it has to be a good thermal insulator. The intermediate layer then is best when it's in the range of the compression heating properties of water and food products, but still has to have a good thermal insulating, good thermal insulating properties. And then we have the innermost layer. Thermal insulating properties, if they are high, that's good, but they don't have to be. But what we do need in this layer is we have to have high compression heating properties, greater than those of water or the food product, and that then gives you an active heating, which further counteracts the heat losses during the process. And then we have a moving piston at the top or on the side, depending if it's vertical or horizontal. That keeps out the cold water or the cold compression fluid, but still allows pressure transmission, and that is made from the same material as the innermost layer, which further improves the temperature uniformity of the process. Again, if you want to read more about that, there's our patent application, the World Patent Application Number. It has now been granted in China, Japan, in Europe, in Australia, New Zealand, and there are further jurisdictions just about to get granted as well. But if you Google for that number here, you will find the patent. There's a lot more details around the setup of this multi-layered canister. So this slide really only shows you how those layers slide into one another. Depending on the target temperature, you could get away with a single or a double layer. But if you talk about pasteurization or sterilization temperatures, you have to go with a triple layer setup in order to get the heat retention. Now coming to the validation trials. So first with the pilot scale canister, so that was the first prototype we manufactured. We used the three plastics I've shown before when I talked about the compression heating properties. Teflon as the outermost layer, polypropylene as the intermediate layer, and polyethylene as the innermost layer. So we used a 35-liter AVR high-pressure thermal sterilization machine. So that actually has temperature capability, but significant temperature variations. But we did run that cold because we obviously wanted to see what happens in a conventional high-pressure machine. So it has a fairly small internal diameter, and the layers, they're each 1 centimeter thick of those prototypes. So that means you lose about 50% of your vessel capacity, but that can be improved upon. So what we looked at is, well, we looked at a whole range of different temperatures, but what I'm going to show here is 90 degrees C and 120 or thereabouts. And we had the compression fluid temperature set to 10 degrees C, so really cold. Pressure level 600 megapascals. We did select the hold time of 15 minutes, and the reason for choosing that long hold time is we wanted to see when does it really start to drop in temperature. And as you can see here, yes, there is some drop over a 15-minute hold time, but over 5 minutes hold time, there is virtually no drop in temperature throughout the vessel. So from top to bottom, there was no drop in temperature. We lose maybe a half a degree in the worst case here. And when we talk about the pressure hold time in a commercial environment, for economical reasons, you would never go to more than 3 minutes, let's say, because it just becomes a too expensive process. But yeah, so if you look at this one here, we reach almost 94 degrees C after compression when we preheat to about 67 degrees C, and we hold that pretty well throughout those 5 minutes. Now, if we go to higher temperatures, yes, there is a more significant drop to be seen, but then again, you need to consider that the temperature gradient from the outside to the inside is about 115 degrees because we go up to 125 here when we preheat to about 94 degrees C. Over the 5 minute period, you have a drop of about 2.5 degrees C. So still pretty good, still over 120 degrees after the 5 minute hold time. And when you have a look here, so as I said, maximum temperature drop 2.6 degrees C. We did CFD modeling studies before as well, and this is exactly what we predicted, a maximum temperature loss in the coldest spot of 2.6 degrees C. Now we then, after we've proven the concept at pilot scale, we went to commercial scale. We built another prototype that fit into one of hyperbaric's canisters. And we did those validation trials then in a hyperbaric 300-liter machine in in Spain. Margarita was actually the one leading that from hyperbaric end. Here, while still 1 centimeter thick layers, the loss of the basket capacity is still in the order of 40%. But we have to consider that the wall thickness hasn't been optimized yet. I've done modeling studies, so CFD modeling of that as well. And the indication is that a 5 millimeter thickness is sufficient as well. And then the loss of the capacity would be less than 20%. But for this purpose here, we still stick with a 1 centimeter wall thickness. And the trials we've done, again, was in the order of 90 degrees C, so actually 96 was our maximum temperature here when we started, just over 70 initial temperature. And as you can see, so whole time here, only 3 minutes to stay within the commercial reasons, let's say, or feasibility. Virtually no temperature drop from beginning of pressure hold time to the end of pressure hold time throughout the whole canister space. So that was very promising. Then at 120 degrees C, we went up to about 120.5 roughly. And as you can see, over the 3 minute hold time, there is a drop of only 0.4 degrees C from beginning to the end of pressure hold time. Again, very uniformly distributed throughout the canister. The reason why it is better here than it was in the pilot scale validation trials is because we have a larger volume to surface ratio, which provides better temperature performance. Now, also here, we've done CFD modeling studies. The prediction was we lose about 0.5 degree C. We lost about 0.4 degrees C. So again, very good agreement. And we have proven that at commercial scale, we can also do pasteurization as well as sterilization processes in a cold machine with our canister. Now, to summarize, I've shown the tools. Well, we've developed more, but I've shown you the most important tools we developed to assess material properties and temperature performance in high-pressure thermal processing. I have shown you the canister concept that we have developed and the validation studies we've done at pilot and commercial scale. So what is happening at this point in time with our partners at Hyperbaric in Spain? We're doing durability tests. So is the structure stable for 1,000 and more runs? So we've done 100 and something at this point in time. Within the next couple of months, we want to reach the 1,000 run threshold, at which point we are then confident that we have a commercial product that can be sold to Hyperbaric's customers. What we will also do once we see uptake of the technology and uptake of our canisters, we will start looking a lot more into optimization. So how much can we reduce the wall thickness and still maintain the temperature performance, so in order to optimize the filling capacity. Now, this is my last slide. This was actually a slide supplied by Margarita. This is how the canister looks like now. So it is still based on the same concept, based on the multi-layer concept I've shown before. Different materials, some of them at least, and a slightly different design. And the different design is because we want to be able to create a system that can be fully automated. Because once you talk about 90 degrees C preheating temperatures, you don't really want to touch that anymore. So manual handling is not really an option. So it has to be fully automated. And in order to do that, we had to redesign, or Hyperbaric had to redesign the canister so that they can be grabbed by a robot and put into the machine and then been taken out at the other end and unloaded. And that is all from me. Thank you very much for your interest in this talk. Happy to answer any of your questions. So just put them in the chat window, and we, over the next couple of days, we will get back to those. You can also just send me an email directly. Happy with either way. Happy to answer any questions. Thank you very much.
Thank you so much, Kai, for the interesting presentation. It is an honor for us in Hyperbaric to work with you and all of our engineering team that we have been working together towards the validation of the canister, like you said. So we are happy to continue towards this path and forward to the commercialization of the technology. So I'm going, yeah. And like I said, everyone, you can just put your questions in the chat, and we will come to those in the upcoming days, okay? I'm going to now introduce Dr. Robert Sevanich. Hi again, Robert.
Hey, Margarita.
So Robert is a research scientist at the Department of Food Biotechnology and Food Processing Engineering, being the group leader of the Food Biotechnology Group. at the Technical University of Berlin. He has been conducted relevant work in the field of high pressure and high pressure thermal processing and its influence on microorganisms, spores, and food processing contaminants in model and real food systems. Throughout this presentation, he will talk about the latest breakthroughs in this field with special insights in food quality and food contaminants produced with HPTP versus conventional sterilization. Robert, I'm going to pass the word to you now. Thank you very much again.
Thank you, Margarita, and thank you for this very kind introduction. And if you can see my slides, I will go ahead with my talk.
Yes,
all right.
Everything's perfect.
As Margarita mentioned, I will be more looking into the food technology side of things concerning high pressure thermal sterilization and why we should use this technology in comparison to thermal retorting. So in the food industry, we have many food degermination processes available, which are mainly thermally driven. And the main aim is actually of all of them to guarantee a certain food safety. If we talk about sterilization, it's the inactivation of spore spell based on the 12D or the 6D concept, depending on what kind of indicator strain you use. But usually to achieve this food safety, we tend to over-process our foods, and therefore we leave out the food quality to a certain extent. And since nowadays the consumer wants more gentler processed foods, we should try to combine these two and align them. But this, to some point, can be quite a balancing act, since we don't want to lose the given food safety for better food quality. So how can we align those two things? How can we combine them? How can we even the scale a little bit? In this case, since with food processing or with the thermal processing itself, we tend to, as already mentioned, to over-process our foods to reach the target temperature inside the product, and therefore we have the possible formation of unwanted food processing contaminants like furan, MCPD esters, and acrylamide. And also we have to take into account nutritional losses along the way as well. So here we need alternative processes like high pressure thermal sterilization. And within the next few slides, I will be talking a little bit more in detail about this technology and why we should use it and how does it affect spores, for example, because we need to look first at food safety and see if we can guarantee a certain food safety with this technology, and later we can try to play around a little bit with the food quality. So the main aim here is also the inactivation of bacterial spores. Spores are highly resistant towards all kinds of different stresses. And even under pressure conditions, we need at least temperatures above 110 degrees C to get feasible inactivation kinetics. Back in 2009, the FDA approved the so-called pressure-assisted thermosterilization, or abbreviated PATS process, where they used the temperature or the reference temperature of the thermal retorting process at 600 megapascals. But back then, this process was listed as a thermal process because pressure was just used to quickly heat up the product due to the adiabatic heat of compression. Back in 2016, the pressure-enhanced sterilization was certified, and here we are now able to use temperatures below this thermal reference temperature of 121 degrees C due to the synergistic effect of pressure and temperature on the inactivation, which was shown in those 7 years along the way in the literature. And the inactivation mechanism for spores is at least a two-step mechanism. And if you look at the spore here in this picture, the main compartments of interest are located in the inner spore membrane, which are the germinant receptors. Those germinant receptors, they code for different nutrients, especially asparagine, alanine, glucose, fructose, and potassium. And the spore monitors its the surroundings to see if those substances are available. And once those dock to these germinant receptors, the entire pathway of germination starts. And another important compartment comes into play, the dipicolinic acid channels, which are also located in the inner spore membrane. And dipicolinic acid makes up 10 to 15% of the dry matter content of the spore core, and it's important for the resistance of the spore. And once the spore made the commitment to release DPA due to the altering of the germinant receptors, it becomes really sensitive to other stresses, and therefore we can inactivate it. Since water comes into the spore, rehydration starts, and then we have the outgrow of the spore, and there it becomes really sensitive. So we need to germinate to eradicate, more or less. So this is kind of a hurdle concept. First trigger germination via high pressure, and then inactivate it with the combination of heat. So, but as we all know, currently there's no application in the food industry. This is probably due to the fact that there's a lack of a sterilization indicator, reliable data and model and real food system is missing, and also the optimization of the existing equipment, although Kai in his talk already greatly showed what innovative ways they are working on, and I think this has a bright future ahead. And let's now look how is the inactivation mechanism on bacillus spores. In this case, this work was done by a colleague of mine, Kai Reinecke, in his PhD, and he looked at different spores, knockout spores which had certain compartments and did not have certain compartments. And if you look here at the spore in a scanning electron light microscope picture here, the bright thing you see here is the D-picolinic acid. And what we can do now with the high pressure is we can alter the important compartments of the spore, as for example the germinant receptors. This is called the non-nutrient spore germination, where we alter with pressure and temperature and make the spore believe that germinants or nutrients have docked onto these receptors. Since these receptors are proteins, they are altered by high pressure, and then the spore runs through the entire cascade of germination. But the sad thing is that we can only inactivate 2 to 3 logs here in this case. So another approach of his was to see, okay, what happens if I increase the temperature and the pressure as well, so to 550 megapascals. And here we see that we have this non-physiological germination. Here we have the release of the DPA, since here in this case we alter the D-picolinic acid channels. DPA is released, we have the partial co-hydration, but then it stops here at the cortex hydrolysis, since probably the cortex lytics enzymes aren't activated due to the lower temperature here. So another approach of his was, okay, let's go again with the non-physiological germination, higher temperatures, higher pressures, and then actually we were able to guarantee a rapid inactivation up to 7 logs and even more than that. And here at this point, as I mentioned, once the spore makes a commitment to release DPA, the rate limiting step at 600 megapascal is definitely the temperature. So we can achieve suitable sterilization conditions using this approach here. This was just to make the the basics clear here and on this part. And also I have to mention, this is only true for bacillus strains. For Clostridia strains, it's a little bit different. Here we need to have the cortex lytics enzyme active before DPA can be released. But this is no problem within the HPTS process, because we have this heat up ramp, and there this activation, this heat shock activation takes place, and then the Clostridia also follows this pathway here as well. So in terms of processing, what it is all about in terms of the center here, this is the main part. We want to lower the thermal load as low as possible. So really fast heat up, really short dwell times if we decompress. And as you can see here in this picture as well, we can, with adiabatic heat of compression, easily heat up, hold it, and then release, and we have a lower thermal load in comparison to the thermal retorting. Also, if we look into the product here, this is the outer region of the product, and here's the center with thermal processing. As already mentioned, we overprocess, and in the center we reach the wanted target temperature to achieve our inactivation, and with high pressure thermosterilization we have a more even distribution of temperature within the sample. And also we have the Le Chatelier principle, which states that under pressure only reactions are favored to have a negative reactant volume. So this means that if we have reactions that have a positive reaction volume, and they usually occur under retorting conditions, those may not occur under high pressure thermosterilization conditions. So this can be interesting in terms of food processing contaminants and also in terms of nutrients. But now, before we go into quality aspects, let's see how spore inactivation takes place under HPTS conditions. And here, those are data I did during my PhD. And we first of all started off an ACEs buffer to test different spore strains and its resistance towards high pressure and high temperature. And what you see here is the temperature time domain for a so-called isokinetic lines for a 5-log inactivation for the different spore strains tested. So along this line, you will always have a 5-log inactivation for the given temperature and time. And what we see here is that especially the surrogates usually used for thermal retorting, like Clostridium sporogenus and Geobacillus stertamophilus, are really high pressure, high temperature sensitive, whereas Bacillus amelicifaciens has a similar resistant towards Clostridium botulinum. I have to mention here that this Clostridium botulinum was taken from literature and also was sporulated at 30 degrees C, whereas the Bacillus amelicifaciens we used was sporulated at 37 degrees C. So this can have an effect on the resistance. The lower the sporulation temperature, the more resistant the spore is. But based on these results, we said, okay, Bacillus amelicifaciens is a non-pathogenic spore former. So let's see how this behaves in salt and sugar solution. And additionally, it has a high temperature, high pressure resistance. So what you see here is we adjusted different water activities for salt and sugar from 1 to 0.9. Again, here you see isokinetic lines. The dashed line is for salt. The solid line is for sugar for 5-log inactivation, Bacillus amelicifaciens. And what we see here is that there is a thermobaroprotective effect coming into play at a water activity of 0.96, which in the beginning, there's not so much difference for low temperatures between salt and sugars. But if you go into higher temperatures here, the difference for salt and sugar becomes more and more pronounced, and is also going the way here to the lower water activities. So you cannot go directly from ACEs buffer system and make your prediction for a real food system, because there are certain ingredients that do have an influence. It is at this point still not known what the exact influence are. This is still under investigation, and happy to discuss this with you in the chat later on. And if we then, based from this knowledge, go into real food systems, and here we tested different fish systems and the baby food system. Again, we did the comparison to Clostridium sporogenus for 5-log inactivation and found lower temperatures are needed under high pressure conditions to inactivate 5 logs. Whereas here, Bacillus amelicifaciens, we need higher temperatures. First of all, there's not a big difference for 5-log inactivation. The thing is that here they merge, but still there's a synergistic effect in terms of inactivation in comparison to here to this thermal border region. So this is also here, if you look at the D values under thermal conditions, much faster inactivation in comparison to HPTS. If we extrapolate this to a 12-log inactivation, we see here actually that here the influence of the food system becomes more and more pronounced, since this is just due to the fact that here the kinetic fit used has a higher influence in terms of the tailing that occurs for the different food systems. And here we nicely see that above here we have the water activity systems that have a low water activity. They are separated by the ACEs buffer, and here we have the baby food system, for example, and the tuna and brine system, which have higher water activities in the range of 0.96, 0.94, and those up here had water activities between 0.91 and 0.92. So a possible process window to get all of those is between 115, 110, and 1 to 10 minutes of treatment time. So we can actually see that we are able to guarantee a 12-log inactivation of Bacillus amelicifaciens. And this is also what you will find if you look into literature, that basically Clostridium botulinum and Bacillus amelicifaciens have similar resistance within the high pressure, high temperature domain, and also that the surrogates that are used also tend to have lower sensitivity towards high pressure, high temperature processes. We have now seen that we theoretically at least can achieve 12-log inactivation and have a food that has a given food safety. But what does happen during processing, let's say with compounds that I don't want? What does happen with food processing contaminants? As I mentioned before, food processed contaminants are unwanted and they are formed during the processing of the food due to the presence of certain precursors, and they do have a negative impact on our health. And many well-known food processing contaminants are furan, MCPDSs, acrylamide. And so here, since the beginning of the new millennium, more and more attention has been given to understand the mechanism and also to have possible mitigation strategies at hand. This is why the EFSA is still calling for continuous collection and occurrence data in food and feed to see what is actually the maximum and in what kind of food systems does this occur. So if we have a look from the chemical point of things, we see here many of the precursors are value-giving compounds, and therefore changing the recipe would not make so much sense. The optimum conditions are at a pH value of 7 and temperatures above 110 degrees C. You will find it in everyday products. And since it's a human cancer again and cytotoxic, the ALARA principle comes into play, which means as low as responsible achievable. But in comparison to the acrylamide here, there are currently no limits or maximum values allowed of furan or its derivatives. But I guess within the next few years, the EFSA might come out with some guidelines concerning this compound as well, as they have done for acrylamide, for example. And if you look into the literature, there were actually only two research agencies who had a look at this, which was Technical University of Berlin and the KU Leuven in Belgium. And they came to the same opinion that the reduction is possible depending on the food system between 71 and 96% in comparison to the benchmark process. And what we have done is we also looked a little bit into the kinetic of sardine and olive oil and the baby food system. And what is quite interesting here is that you see that double the amount is formed of furan in sardine and olive oil in comparison to the baby food puree. Although we use the same temperature time combinations. And this is due to the fact that different precursors have different tendency to form furan. And in the case of sardine and olive oil, we saw that there, of course, are in the olive oil polyunsaturated fatty acids in the sample, which have a higher tendency to form furan, as, for example, the carotenoids or the sugars within the baby food system. But nevertheless, in comparison to the retorting we applied, we were able to reduce the amount between 71 and 97%. And this was also validated in a recent project we just finished, where we also looked into the formation of furan and its derivates in chicken vegetable rice puree, which is also suitable for the baby food application. And here, under HPTS conditions, all of those conditions here lead to a 12-log inactivation in this food system of Bacillus aemiliifacins. We did not find any formation of furan or derivatives, but in the benchmark process, we did find especially 2,5-D-methylfuran to high extents. And if you compare this here to a similar process, but under pressure, we see that there's no formation at all. So only the lower thermal load applied to the product cannot be the reason that lower formation of furan occurs. And this was something that was of interest to me and which I looked into. And if you look at the formation pathway here of furan, you see that many of those reactions involved in this pathway actually can take place since they have a negative reaction volume. And I did not find anything about this dehydration step here. So this dehydration step, it could be the rate limiting step in this case, but actually more questions popped up. How toxic are intermediates and how stable are those? Does a negative delta V mean that the reaction will take place, or does pressure have a retardation effect? Because the formation occurs under pressure conditions, but it's not as severe as under thermal conditions. So this is still a question that needs to be answered. But I think we are on a good way there to understand the influence of high pressure thermosterilization on the formation pathway here. And this brings me up to the influence on other quality parameters. For example, a lot of was done for carotenoids, especially also here KU Leuven and TU Berlin in cooperation with the BOKU in Vienna. And basically the main, the common denominator here was, depending on the food system, there's either no change of beta-carotene or there is a loss for thermal retorting around about 31-28%, whereas for HPTS, there was only minimal nominal amounts reported. For example, here 7%, here 9%. So better overall. Quality in terms of retention of carotenoids. If we now look into the color of food, the color of things, since the color is the first thing that the consumer comes into contact with if he sees a product, and so this is a huge selling point. Here also a lot of work was done for different food systems, and here also the main take-home message is that the color can be retained better via HPTS treatment in comparison to thermal retorting, smaller delta E values, or no changes at all. This was also something we saw in a recent publication within a project, together also again with the BOKU in Vienna, where we looked at the color changes for the mentioned chicken rice puree, and here we saw that for the delta E for thermal retorting, we had a delta E of 6, and for the HPTS treated products, we had a delta E between 2 and 3. So still visible for the trained eye or the human eye, but still lower as in comparison to the thermal retorting. So smaller impact. And this brings me to the conclusion of my talk. So we should do more inactivation studies in other food systems, since I think it still will be a case-by-case approach. Screening of spore strain under defined natural sporulation conditions to finally have an indicator strain. Scale-up trials, which I did. I was lucky enough to be working for a week at the 55-liter system at the IATSTI in Bilbao. And there we showed that basically in terms of food safety, we did storage trials, so challenge studies, formation of food processing contaminants, and also in terms of colors, there are no big difference. So we have a dual benefit, since we guarantee food safety and we have the reduction of the toxicological potential with a gently processed, safe, high quality product in the end. Questions for the future and for research are characterization of post-treatment effects. So what happens during storage if we apply this technology? Then the question of the packaging material, since nowadays also with HPP, they're shifting into mono or B-layer packaging to meet European 2020 recycling targets. So what kind of polymers should we use? PA, PE, PET, combinations of those. And then, of course, the biggest questions, which I think was answered today by Kai, is the system design. But after hearing his talk, I'm not worried that this will be implemented very, very soon. So high pressure thermostabilization offers a huge variety of different positive effects on our foods. And those were the references I used. And I thank you for your kind attention. And if you have any question, you can directly put them in the chat. We will answer them within the next few weeks, or email me directly. Both is fine by me. And again, thank you, Hyperbaric, for having me.
So thank you so much, Robert, for the nice presentation. I think we have some time to go over some questions of the chat. So if you don't mind, I'm going to maybe do 2 questions each to each one of you. Okay. Maybe we can start with you, Robert.
Yeah.
So what are the indicators we should focus on to ensure food safety with HPTP?
Yeah, this is a very interesting question, Margarita, and heavily discussed under researchers. And so back in 2009, when the FDA approved the PATS process, it was approved based on the 6-log inactivation of Clostridium botulinum in mashed potatoes. So I think in the beginning of this technology, I think there's no way around Clostridium botulinum, but as Kai has shown really nicely in his talk, we can actually use the 3 minutes at 121 degrees C. We have the preheating, we have the dwell time or the pressure buildup ramp, the dwell time. So overall still, let's say 15-20 minutes of processing, which is still much shorter in comparison to the thermal retorting now, and therefore we still have those benefits, which I also shown in terms of formation of food processing contaminants, carotenoids retention, color retention, etc. So and I hope that in the near future, when we know more about this technology on industrial scale and have done probably challenge studies, storage trials, we then could use the results I've shown and the process windows we have gained for Bacillus acidophilus and apply those for the products as well and see how they will behave. But I think in the beginning, there will probably be no way around Clostridium botulinum.
Yeah.
At least this is my personal opinion.
I think we both agree. I can see Kai.
Absolutely.
Yeah, thank you very much for the answer. Maybe I'm going to jump to Kai. Quick question, very interesting, and you talk about this. Will the thermics be available to the industry? And you talk about the algorithm, the clever algorithm you had to develop. So what do you feel about this? Can people do their validation in their
What do I
facilities?
feel about this? Coming to your first question. So yes, in principle, they are available to industry already. And we have one client at the moment who has used them to validate their process for some time now. The downside at this point in time is that the software and the algorithm you were referring to as well, which does the prediction of the temperatures outside the thermoeggs based on the readings within the thermoegg, is not available to industry. It's too complex, a specialized software package that we have here at CSIRO. So the model we are currently working on with that one client is that they send the data to us, we do the corrections, and then send them back to them. And that's exactly how we, Margarita, you and I worked around the validation of the canister as well. So if the demand increases, though, for those thermoeggs, so let's say we commercialize the technology, people needed to validate their process, and there are too many for me then to do those corrections every time, there is probably justification then for me to develop a software package that can be made available to the industry as well.
Yes, that's nice. Yeah, we hear it at Apravaric when we did our validation, and we are still doing it. Every time we did a trial, we send the results back to Kai, and he would forward us the corrections, and we would work alone together in this way. Thank you very much. I'm going to jump now to Robert, and this for me is a very interesting question, and it has a lot to do with the food contaminants that you spoke about. So what's your opinion on the future of the technology? In which application do you see the most potential?
Yeah, also really a good question. And I think in the beginning, we have to focus on high quality product that contain a high amount of nutrients or are made for sensitive and vulnerable consumer groups. And there I'm thinking of parenteral nutrition and especially baby food systems. Since, as mentioned here, we have the sensitive consumer groups. They are quite costly products. So here, in terms of processing costs, this would not make such a big issue here. And especially if we talk about the baby foods sector here we have a group that has a low body weight, and if it consumes a lot of those products containing furans, they are easily affected by this. And the results I've shown are just the tip of the iceberg. If you go into literature, there have been many studies looking into different baby foods in Europe, and they have shown 20 to 15 times the amounts of furan in those food systems. And if we are able to reduce the amount in those systems by 90%, I think this is a really, really good way. And of course, if the EU or the EFSA decides to put out guidelines and maximum amounts of furan or other compounds formed within the products, which are not out now, but which I think will come in the near future, then mitigation strategies are needed, and then HPDS could be key in solving this. And then, of course, I also think Kai mentioned this a little bit in his talk. I think let's say a high pressure intensified pasteurization, maybe for juices, for example, where we can go with 600 megapascals, 80, 90 degrees C, 1 or 2 minutes of holding time to be able to cope with the Alicylobacillus acidoterrestres, which is sometimes a big issue in juices. And some organizations even want to have zero tolerance on this one. And then also you will not have the issue of the enzyme activity as well. So I think in terms of products, it should be at the beginning high quality, high nutritional products, and then in the end I hope that there will be convenience products that will follow, like pasta, sauces, dips, ready to eat meals, and so on. So I think it has a bright future, but we will have to wait a little bit, I guess.
Yeah, definitely. But I feel the same thing. I think baby food, it's very big application to be used in a technology, especially because it is a growing market, and we can see with HPP we have been increasing the baby food products processed with HPP so much for the last years, And I think it's a very growing trend. So definitely we can use technology in the future. We hope so.
Yeah.
It's funny
Thank
that you mentioned baby food, because one of our clients is a baby food manufacturer, and they're just waiting for this technology to go commercial, to do high pressure, high temperature processing.
Yeah, that's nice. I think we definitely are going to have a boost in this area in the upcoming days. Not upcoming days, upcoming years. So everyone who is thinking about it, I think it's predicting the future. So it's very clever from their end. Yes. So let's go to the last question. This one is for Kai. I think it's what everyone is thinking about. Will the technology be economically feasible? What are the main setbacks? Is there any cost estimation?
Well, you ask the inventor of the canister. Of course, I say yes, it's economically feasible. But it's a good question, though. It's important to note that while we are almost at the end of the R&D phase, we are still within the R&D phase. So it's not commercial yet. It's not industrialized yet. So as you will appreciate, the canister will require a complex handling system, which incorporates preheating and handling in a fully automated way. So you have robots putting it in the preheater, assembling the canisters, putting the product in, closing it up, bringing it to the machine. So it's not cheap, let's say. But is it cost effective? I believe yes. So, I mean, you guys at Hyperbaric, you have looked at that in more detail than I have. But when you, in discussions, if I understood that right, when you compare that to a 300-liter HPP system, a conventional one, and you would now want canisters and the preheating and the handling system, you'd add about 75% on top of the cost of a high-pressure machine. So from a capital expenditure perspective, yes, it is still expensive. Will you get a much better product? Yes, I would think so.
Definitely.
And so from a cost per kilogram perspective, I assume this would be in the order of 20 euro cents per kilogram. So again, slightly more expensive than HPP, conventional HPP, because you require the preheating. But once we get into the stage of proper commercializing the technology, then obviously analyzing the economics is a lot easier than saying this at this part of the R&D phase. So we go commercial, I have no doubt. Will it be cost effective? I think yes, but only the future will tell.
Totally, definitely. Thank you for the answer. And yeah, we are confident that we can stay below the 20 cents per kilo. Let's see. Like you said, we are in the R&D phase, so I think we still need to know what the cost will be when we are producing a lot of canisters, when we have a lot of clients, which we hope it will be the future. Like we said before, there is a lot of potential to the baby food industry, and which is an industry with a lot of economical power. So I believe we can definitely make this economically feasible. But let's hope for the future, and we will let everyone know. There is the chat. You can put your questions there, and you can continuously to ask us for more updates and feedbacks. Each one of us will be happy to answer all of your questions and to keep you updated on this process. So thank you very much to all of you, to the audience, and to Kai and Robert for the very interesting conversation. I am going to finish the conversation now, and that's it. Thank you very much. So bye, guys. Bye, everyone.
Bye.
Bye.
Bye.